We have seen how we extract metals from their ores. Now let's take a particular example, an example of aluminium. Let's see how we extract aluminium from its ore. The ore that we use to extract aluminium is bauxite. Bauxite is Al2O3.2H2O. This is the ore that we use to extract aluminium. We know the first step is to get the concentrated ore itself. So we have to crush the ore, grind it, and then remove the gangue particles by using different techniques like hydrolytic method, magnetic separation, and froth flotation method. Once we get the concentrated ore, now our aim is to get the oxide from this concentrated ore. The oxide is used for the extraction of metal. So we always try to convert the ore into its oxide. So now we have the concentrated bauxite ore. We have to convert it into oxide. Let's see how we do that. So we have bauxite. We make it to react with NaOH, that is sodium hydroxide. So when bauxite reacts with sodium hydroxide, it forms NaAlO2, that is sodium aluminate, and water. Then we take sodium aluminate. It is made to react with water. It forms sodium hydroxide back and a white precipitate of aluminium hydroxide. So this is the technique to get aluminium hydroxide from bauxite. This is a white precipitate. Now from aluminium hydroxide, it is very easy to get the oxide of aluminium. So we simply heat aluminium hydroxide, but the temperature is very high. So we have to heat aluminium hydroxide at 1000 degrees Celsius. It forms aluminium oxide, that is alumina, Al2O3, and it forms water. So from concentrated bauxite ore, our aim was to get the oxide of aluminium. So from bauxite, we use sodium hydroxide to get sodium aluminate. Then from sodium aluminate, we get aluminium hydroxide. Then we heat this aluminium hydroxide at 1000 degrees Celsius. It forms the oxide of aluminium, which is known as alumina. So now we have the oxide. Our next step is to extract the metal from the oxide. That is, we have to remove oxygen from oxide. That is, we have to carry out the reduction of the oxide. So we have to carry out the reduction of the oxide, in this case alumina. You remember the metal activity series that we have seen? Aluminium can be extracted from its oxide by electrolysis. So for aluminium, in order to extract it from its oxide, we have to carry out electrolysis. This process of electrolysis for aluminium was first carried out by two scientists, Hall and Heroult. Both of them carried out the electrolysis of alumina to extract aluminium. In this process, we take alumina. So alumina decomposes or dissociates to give Al3+ and O2-. In this electrolysis process, they also used two other electrolytes. The first one was fluorspar, that is CaF2. CaF2 dissociates to give Ca2+ and fluorine ions, that is F-. And the other electrolyte which was used is Na3Al(F6), that is cryolite. This dissociates to form Na+, Al3+, and F-. We have to extract aluminium. We used alumina. Now we have to carry out the electrolysis of alumina in order to extract aluminium. So why did we use these two other electrolytes? We'll see why we use these two other electrolytes. But right now, electrolysis was carried out by using these three electrolytes. So now in the electrolytic solution, there are three positive ions, Al3+, Ca2+, and Na+. Again, there is Al3+. So there are three cations. And we know only one cation can be discharged at the cathode. Based on the position of the ion in the electrochemical series, we decide which cation is discharged at the cathode. So we have Na plus, Ca2 plus and Al3 plus. So we know the ion which is lower in the electrochemical series is discharged at the cathode. So in this case, Al3 plus lies below Na plus and Ca2 plus. So Al3 plus is the cation which is discharged at the cathode. So the reaction taking place at cathode is Al3 plus. Since it has 3 electrons less, so it takes up 3 electrons to form neutral aluminium. This is how we extract aluminium from its ore, bauxite. Now if we look at the anions present, there were 2 anions, that is fluoride and oxide, O2 minus. The halogens lie in this part of the electrochemical series, and the oxide or the hydroxide ion is always lowest in the electrochemical series. So again, based on the relative position, we know that oxide ion is discharged at the anode, and the reaction taking place is oxide ion is discharged at the anode. It loses 2 electrons to form an oxygen atom. This single nascent oxygen atom is not stable on its own, so it combines with another oxygen atom to form oxygen gas, that is O2. So oxygen gas is released at the anode and aluminium is formed at the cathode. So the aluminium which is extracted in this manner is 99.8% pure. So we further do not have to refine the metal, as by using Hall-Heroult's process, the aluminium which we get is 99.8% pure. Now the question is, while carrying out this process, we used 2 other electrolytes. Why did we use those 2? Let's try to answer that. CaF2, this is used to increase the conductivity of alumina. Alumina itself is a non-conductor of electricity, and we know for electrolysis to take place, we need a good conductor. If we only use alumina, it will not conduct electricity, and hence aluminium cannot be separated. So we use CaF2 to increase the conductivity of alumina. Now why did we use Na3AlF6, that is cryolite? This is used to bring down the fusion temperature. Had we not used cryolite, the reaction would have taken place at 2050 degrees Celsius, which is a very high temperature to attain. So in order to bring down the temperature from 2050 degrees Celsius to 950 degrees Celsius, which is a temperature that can be attained, we use Na3AlF6. So in Hall-Heroult's process, 2 other electrolytes, that is other than alumina, are used. Those 2 are CaF2 and Na3AlF6. Both of them have special purposes. CaF2 increases the conductivity of alumina, and Na3AlF6 brings down the fusion temperature. And hence, we use these 2 electrolytes in the Hall-Heroult's process. What is the purpose of CaF2 during the electrolysis of aluminium oxide? So CaF2, it increases the conductivity of alumina, that is Al2O3. We have to extract pure aluminium from alumina. If we carry out the electrolysis of alumina itself, this is a non-conductor of electricity. So to make it a conductor of electricity, we use CaF2. So CaF2 increases the conductivity of alumina. So let's revise how we get pure aluminium starting from its oxide and starting from its ore, which is bauxite. So we have the ore bauxite, which is Al2O3 dot 2H2O. So from this, we use the Bayer's process, that is, we use NaOH. So how NaOH helps us? It reacts with bauxite to form sodium aluminate and water. This sodium aluminate further reacts with water to form the white precipitate of aluminium hydroxide. And this aluminium hydroxide is a white precipitate which, when heated to 1000 degrees Celsius, it forms alumina, which is an oxide of aluminium. So our first aim of getting the oxide from the ore is fulfilled. So we get the oxide ore of aluminium using the Bayer's process. Now our second aim is to reduce this oxide to get the pure metal. In this case, we have to carry out the reduction of alumina. In the metal activity series, we see that aluminium, for the reduction of aluminium oxide, we have to carry out electrolysis. So we carry out the electrolysis of alumina. This process is known as Hall-Heroult's process. So from Hall-Heroult's process, when we carry out the electrolysis of alumina using two other electrolytes, that is CaF2 and Na3AlF6, we get pure aluminium. This aluminium which is obtained is 99.8% pure. So starting from the bauxite ore, we get the pure aluminium metal. This is how the extraction of aluminium is carried out in industries. It is very important to get pure aluminium as we need it for different purposes, like aluminium is used in the electric cables for making aluminium foils and so on. So we have seen how we extract pure aluminium from its oxide, and the oxide is obtained from the ore bauxite.